Hello guys, welcome to another video. Today we're going to work at topic 9 for HL wave phenomena. So we're going to solve a couple of problems. So let's jump straight to the paper and see the solutions. So the first question, it says that you have a cone and a dust cap D of a loudspeaker L that vibrates with a frequency of 1.25 kHz with simple harmonic motion. 13b. Define simple harmonic motion. As we have seen already, this is a definition that you usually meet, so we have to be very careful here and don't lose any marks. So what do you say here? How you define that? Simple harmonic motion is the motion in which the acceleration or the force, any term here is acceptable, is proportional and in the opposite direction to the displacement from a fixed point or from an equilibrium position. And this is how you define the simple harmonic motion. You have to state that it's proportional and of course you have to state the direction. This is how you get these 2 marks. 13c. D has mass of 6.5 times 10 to the power of -3 kilograms and vibrates with amplitude of 0.85 millimeters. Calculate the maximum acceleration of D. So number 1, super simple, what we need to do, calculate the maximum acceleration that is given by this formula, minus omega squared times A. Now, of course, here you are missing omega, but what you can do is to calculate omega, it's 2 pi f, and you have the frequency, 1.25 kilohertz. So doing your math here, the calculations, you are going to find omega of 7,854 radians per second. So you are going to apply this at your formula. You have the amplitude 0.85, and if you do the math correctly here, you are going to have a value of minus 5.2 times 10 to the power of 4 meters per second squared when you round the number to 2 significant figures, as you can see here also. And number 2, determine the total energy of D. Here again, something very simple. The total energy, it will be given by this formula. All these formulas are in your data booklet, so don't worry about it. You can easily find them. You have everything, omega, A, mass, whatever. If you do the math, you are going to find a number of 0.14 joules. Again, rounded to 2 significant figures. 13d. The sound waves from the loudspeaker travel in air with speed of 330 meters per second. Number 1, calculate the wavelength of the sound waves. Now, this one again, very simple. You use this formula for the speed, that is lambda times f. So you're going to solve for the wavelength, that is v over f. You have everything here. The velocity is 330. The frequency is 1.25 kilohertz. So if you do your calculations here, you're going to find 0.264 meters. But be careful, we don't want that. We want to round this number again to 2 significant figures. So this is going to be 0.26 meters. And number 2, describe the characteristics of sound waves in air. So you see that you have 2 marks here. 1 mark is for your calculation, 1 mark is for the characteristics of sound waves in air. Here is nothing much to say. The sound waves in air are longitudinal waves, with some small mistakes here in grammar, but who cares about that? 13. A second loudspeaker S emits the same frequency as L, but vibrates out of phase with L. The graph below shows the variation with time t of the displacement x of the waves emitted by S and L. And number 1, deduce the relationship between the phase of L and the phase of S. So what do we see here for the number 1? You see that the S, it's whatever happens to S, after a while it happens to L. So it reaches the maximum oscillation before L. So S leads L, but for how long also? You see here is the difference. You can see it between the 2 maximum points, for example. And this value, based on the graph, it is 0.1 milliseconds for 0.1 milliseconds. Or you can state in terms of period, it's 1 over 8 and so on. Number 2, on the graph sketch the variation with t of x for the wave formed by the superposition of the two waves. So what we have to do here is to create the superposition of these two waves. So what you have to do, at every point you have to add the individual amplitudes. So of course you see here, at this point, it's gonna give you the maximum amplitude. And how much it's gonna be? Here you can see that each one individual ones, they have 0.8. So the maximum, it needs to be double this number. So it's gonna be 1.6. So you are here. So this is gonna be the maximum point. Then the 0 point, it's gonna be of course between those two. When you have the one at a positive value, the other one will have a negative value. So this one is somewhere here. The same happens to this one. This is your maximum point, that is here, and so on. So these are all your points that you need to connect for the maximum amplitude. So this is how it will look like. And this is the superposition of both waves. Now the next question is about diffraction and resolution. Monochromatic light is incident on a narrow rectangular slit, as you can see here from the graph. The light is observed on a screen far from the slit. The graph shows the variation with angle theta of the relative intensity for light of wavelength 7 times 10 to the power of negative 7 meters. Estimate the width of the slit. So what do we see here? The first minimum occurs at an angle theta of 0.05. Also you have the wavelength, so this is something very simple to do. You use this formula that the angle theta is equal with the wavelength over the width of the slit. You solve this one for B, so it's the wavelength over the angle theta. The wavelength is 7 times 10 to the power of negative 7 meters, and the angle theta is 0.05 radians. So if you do the math here, you're going to find a number of 1.4 times 10 to the power of negative 5 meters. The next one says, on the graph, sketch the variation of the relative intensity with angle theta when the wavelength of the light is reduced. So what do we see here? We see that based on this formula from before, B is equal to lambda over theta. When you reduce the wavelength, then of course the angle theta needs to be reduced as well, because the width of the slit, it stays the same. So here in the graph, I'm gonna sketch the exact same pattern, but of course narrower. The angle theta, it will be smaller than before. So it will look like something like that. Now where exactly you put the angle theta, it doesn't really matter. So it looks like so. The next question is about diffraction and interference. The light of wavelength 620 nanometers from a laser is incident on a single rectangular slit of width 0.45 millimeters. After passing through the slit, the light is incident on a screen that is a distance of 3.4 meters from the slit. Calculate the distance between the center of the first minimum of the diffraction pattern. As we can see, here the light is gonna come, it's gonna be incident on the screen, and we try to find the distance of the first minimum. So somewhere here it will be your first minimum. So our first step is first of all to calculate this angle theta. And then I'm gonna use geometry in order to calculate this distance, let's call it S, after I have this one. So in order to calculate the angle theta, I'm gonna use this formula, of course, the wavelength over the width of the slit, and you have everything here. 620 times 10 to the power of negative 9 meters is the wavelength. The width of the slit is 0.45 times 10 to the power of negative 3 meters. So if you do the calculations here, you find an angle of 1.4 times 10 to the power of negative 3 radians. Now, what do you know? You know that for small angles, as you can see here, of course we are going to use a trigonometric function here, the tangent of theta, it's going to be the opposite over the adjacent. The adjacent is this length here, let's call it y, it doesn't really matter. But for very small angles, this tangent, it can be excluded. So theta is equal to S over Y. So from here, you're looking for S, so it's theta times Y, and the theta, it's 1.4 times 10 to the power of -3. The Y, it's 3.4 meters. So if you do the calculations here, this distance, it will be 4.7 millimeters. We need to create again two significant figures, so this is gonna be your answer. And also, don't go out of the box as I did. Okay, include everything here. 18b, the laser in A is replaced by two identical lasers so that the light from both lasers illuminates the slit. The lasers are both 6 meters from the slit. The two diffraction patterns on the screen are resolved according to the Rayleigh criterion. Number one, state what is meant by the Rayleigh criterion. So this is something very simple. Again, it's a definition. We have to know about that. So you have to say, in order of these two images to be resolved, what do you need? You need the first minimum of the one diffraction pattern coincides with the central maximum of the other diffraction pattern. And this is the Rayleigh criterion. And number two, it says, the minimum separation of the two laser beams is x. Determine this x. So the minimum separation from before, from 18a, okay, we saw that here we need to have the angle theta that is 4.7 millimeters. So for the minimum separation, you need to have this specific distance. Okay, so now here I'm going to use a little bit of geometry. So this one and this one, it needs to be equal with this one and this distance 1, the separation between the lasers. So from geometry what we have the x over the 6, so this distance over 6 is equal with this distance 4.7 millimeters, so times 10 to the power of -3 over this distance 3.4 meters. So doing this calculation here, you're going to find a number of 8.3 millimeters. And this is the minimum separation of the two laser beams. Number 19 is a question about the Doppler effect in sound. So it says that a fire engine is traveling at a constant velocity towards a stationary observer. Each siren emits a note of constant frequency. As the engine passes close to the observer, the frequency of the note perceived by the observer decreases. Explain this decrease in terms of the wavefronts of the note emitted by the siren. So what do we have here? We have the frequency is higher when it approaches because more wavefronts received. Also we have the frequency lower when it recedes because you have less wavefronts received. And we're going to create here a sketch in order to show that. So this is the source that it emits the wavefronts, these are the wavefronts, and of course they're gonna look like so when it moves in this direction. So here more wavefronts, here less wavefronts received. And 19b, it says the frequency of the note emitted by the siren is 400 Hz. After the fire engine has passed, the frequency of the note detected by the observer is 360 Hz. Calculate the speed of the fire engine. Take the speed of sound in air to be 340 meters per second. So of course here we're going to use Doppler's effect. So the new frequency that you get is equal with the old frequency times the speed of the sound in the air divided by the speed of the sound on the air plus the speed of the source, because we have a moving source and a stationary observer, plus, of course, because it passes through. So it passed through, so it recedes. So if you do your calculations here, you will have to solve for the velocity of the engine. So you have v times f divided by f prime minus v. So this will give you an answer if you do the calculations of 38 meters per second. Okay, nothing hard here, just the application of the formula. Be sure how you apply the Doppler's effect using stationary observer or stationary source, whatever it's necessary to use, plus and minus sign. So that's all for today, guys. You need to study hard and good luck.